Hi, everyone. Can you guys hear me?
Yep.
Good. Okay, so we start now. For today's review, there are 3 sections: introduction, Bayesian, and the linear descriptive function. For the BDT and the LDT, I will first review the concept and then go through some practice question, which is already posted on the tutorial. And also these slides, my slides is already posted on the tutorial. Also, you can download it and go through it with me. Okay, so also if you guys have any question, like just type in the chat or just unmute yourself. Okay, for the first section, introduction section, what is pattern recognition? We take lots of raw data as input, then we try to find the pattern or extract the feature from those data. All actions are based on the categorize of the pattern. This process is called as pattern recognition. The pattern recognition system has 7 steps. The first step is input, so it's taking all unorganized raw data. Second step is sensing. The process of collecting, that's the process of collecting all those data into the pattern recognition system. For example, we use the camera, temperature sensor, or kind of sensor to collect the raw data. That's the sensing steps. And the third one is segmentation. Segmentation is the core step, which is try to identify the meaningful segment as samples. For example, we use a camera to take a picture of a human face. Then when we do the face recognition, we want to segment the photo pixels first, and then to identify which pixel is important enough to decide whether it's a face or not. So that's the core step. The fourth step is feature extraction. We want to find some feature that can distinguish a pattern from another. So also the feature is the feature are in variance. That's important. And the next is classification. So based on the feature we already extract from last step, we classify the input data into category in this step, in the classification step. Next is post-processing. Based on the result of classification, we calculate the error rate of the classification. And then based on the error, we make some improvement to the previous model we choose. For example, we found the error rate is too high, so we decide to change the decision boundary or change the features. We make some change during the post-processing. The final step is decision. So in this step, we just output all the pattern, we just output the result of this pattern recognition system. So we need to, for this part, we need to remember all the name of each step actually is open book. So you need to just find this slide maybe during the midterm. Okay, and next. This course also introduce us a design cycle, which consists of 5 steps. It's collect data, choose features, choose models, train classifier, and evaluate classifier. The second and the third steps require prior knowledge to make good choice of feature and models. These two selection heavily affect the training result. Also, the last step, the evaluation step, is used to evaluate the selection of these two. We use the last step to evaluate the feature and the model we choose. Okay. There are two important definitions. The first one is overfitting. Overfitting means our selected feature and the model perform well on the training set, but perform badly in unseen samples, which we don't want. We don't want that. We don't want the overfitting. The second definition is generalization. It means the model we choose performed well on both training set and the unseen sample. That's what we want. So therefore, we want our model to have generalization, not overfitting. The last topic in the introduction part is the type of learning. There are three types: supervised, unsupervised, and semi-supervised. So supervised learning means the training data contain the labels. And unsupervised means the training data does not have the labels. So that's the key difference. And semi-supervised learning means it's in between. Partial training data are labeled and partial are not. So that's in between. Yeah, I think that's all for the introduction part. And then we go into the Bayesian decision theory. So this theory is to classify the unseen data based on the probability. For very general case, we have two class. For example, we have two class, W1 and W2. We want to, and we know the probability of each class. P, for example, we know there are two class, W1 and W2, and we know the PW1 and PW2. That's the probability of each class. And we call this kind of probability as prior probability. And then we have an observation X, and we know the distribution, distribution of X in each class. We call it likelihood. So it's the probability of X, given that the class equal to W1 or W2. That's likelihood. So we know these three, and we want to know, given X, what is the probability of that X belong to class 1 or class 2. This conditional probability, we call it as posterior probability. That's the one we want to calculate. Okay, so we can calculate the posterior probability of W1 and W2 given by X by the Bayesian decision by this formula. So because we already know the likelihood and we know the prior probability, they are always given in the question. And for the denominator, we can calculate by the sum of the joint. This part, we can calculate by the sum of the joint probability. Summing up the joint probability of W1 and X and the joint probability of W2 and X will give us the total probability of X. Okay, so we can replace the, actually it's, what I'm saying is like the denominator is and we can just replace this joint probability by the likelihood and prior probability, which we already know. Therefore, the posterior probability can be calculated by this formula. Okay, so how to classify it is we calculate the posterior probability for both class and make the classification decision based on the value of the posterior probability. If the posterior probability of class 1 is higher than the class 2, which means given x, the probability being class 1 is higher. So we classify this x as class 1. Otherwise, we classify it as class 2. If we need to set a boundary between class 1 and class 2, the boundary value should make the posterior probability of class 1 equal to posterior probability of class 2. So if we want to set a boundary, these two parts should be equal. We also can write it down as because the denominator is always the same. So we can write the formula as this one. These two are also the same. Okay, and we also can view the posterior probability of each class as a discriminant function g. So we can always write g equal to like this. If G1 if G1 is larger than G2, so we choose class 1. Okay, for this section, that's the formula for this basic formula for the Bayesian. And for this section, we also consider the case that distribution of each class is Gaussian distribution, which means the likelihood is Gaussian distribution or the multivariance Gaussian distribution. If we write, if the likelihood is Gaussian distribution, just single variance. So 1D Gaussian distribution, we can write down the probability formula. Also, the likely formula is this one. The mu is the mean, and the sigma is standard deviation. The sigma square is the variance. So here is the sigma, and we always write down as use the sigma, plug in the sigma square into the Gaussian. We usually write the Gaussian like this. Okay, this one is 1D Gaussian. And if the likelihood is multivariance Gaussian distribution, we can write down the formula like this one. This formula are also in the course note. So you don't need to remember it, you just need to find it. Okay, and first one, this one is also, the mu bar is also the main, but it's a vector because there has a that's for the multivariance, means there has more than 1D Gaussian. And that's a vector. and this one is a matrix. So the mu bar is a vector of means, and the second parameter is the covariance matrix. And here it's the determinant of the covariance matrix. And the D in here means number of features. And X is observation vector. Okay, and here, this one is just the inverse of covariance matrix. That's the formula. Okay, so if we want to write the discriminant function, the G function, for the multivariate Gaussian, it has 3 cases. The first case is multi-dimensional Gaussian. There are 3 cases. The first case is each class has independent features with identical variance. Means the each covariance matrix can write as so that's the first case. The second case is that each class has the same covariance matrix, just matrix 1 equal to matrix 2, but they can be, for example, it can be this one. Or we can write the first case like this. So it's always come from identity matrix. However, the case 2 doesn't need to come from the identity matrix. Only the standard for the second case, just each class has the same covariance matrix. That's it. But the first one is it needs to come from the identity matrix. The third case is just very general case. Each class have different covariance and nothing is the same. So the G function, actually the formula for G function for each case are the same, but if we plug in this number into the G function, we can derive the G function for each case. We can derive an equation for each cases. It's a simpler equation. The function I didn't provide there. The G function for each case I didn't provide here, but it's in the notes. So you guys can try to derive G function for each cases, and the steps are also in the class note. And here I just want to just say again to see the difference between 3 cases. For the first case, it's the equation of covariance matrix is like this. And is the covariance matrix is same for all classes? Yes, it's the same. And is there a covariance between the features? It's no. The second case, all covariance matrix are the same. Or I can write it like this. So it's always the same for each the covariance matrix always the same for all classes. And there has a covariance between features, because if one covariance matrix change, the second one are also change. For the 3 case, it's just everyone has their own covariance matrix. So there's not the same. And is there the covariance between the matrix between the features? Yes. So that's the difference between 3 cases. And you can, from the question, we will always provide the covariance matrix to you. So you can decide which case it follows from the covariance matrix we give to you. Okay. Right now let's go to see the practice question for this one. I think you guys also get the questions in the DGL. Let's see. Okay, I just write down the steps in here. Okay. For the first question, they give us 3 types of meal. So there has 3 cases. It's seafood, vegetarian, and meat. There are 3 cases, and we have an observation. X is whether poison or not. That's the observation. And now we know a person. Now we want to know is a person is poison or not. So we want to let's put it that way. Now we know a person is eating meat, and we want to know whether the person is poison or not. We want to find the posterior of eating meat, and it's already poison. That's what we want. And we need, for calculate this one, we need the Bayesian formula. So it's likelihood prior evidence. The Bayesian formula is like this, and we know the likelihood and the prior is given to us. For the prior is for seafood is 40%, so it's 0.4. Vegetarian is 0.15. Meat is 0.45. The prior is already given to us, and likelihood are also given to us. When the S means seafood, and P means point. I just write it all down. Okay, so these are all given by the or given in the question. So we just plug in the number to this formula. The only thing is we want to get the evidence. Evidence is the total probability to get poison. So for each case, we want to do the the evidence will be for evidence, we just adding up for each cases. For each case is likelihood multiplied by its prior and just sum all the case up. And we will get the evidence. So we just plug in this part into the evidence and plug in the likelihood for meat. So this one should be poison meat and prior of meat. Then we will get the final posterior posterior probability for meat. I just leave the calculation part to you, but the equation already here. So the denominator is this part, and the upper part is here. So here already has the formula. We actually for the answer we need given x, and we want to know what's the probability that given x and the person already eat meat. And x is poison or not. So yeah, here you can just write down replace the poison as x. So we want to find it's already poison, and what's the probability of that person is already eat meat. Is there any question for this one? Okay, we go to next one. Okay, next one is we have, so suppose X is one dimension feature. And we want to design, and it gives us it's one dimension, so, and it gives us a Gaussian. So we know it's 1D Gaussian. Usually we use this formula. And from the question, we know the mean is -1, Okay, I write down in here. Sorry. For the likelihood for class 1 has the mean as -1, covariance is 5. Likelihood for class 2 mean is 2 and covariance is 2. That's given to us. So likelihood already given. And the first question is stretch the 2 likelihood density on the same graph as the function of x. So the question want us to just draw these 2 likelihood in the same graph. The graph of Gaussian is based on its mean and its covariance. So let's draw. Let's first draw for the class 1. We know the mean is -1. So we know the for class likelihood of class 1, the mean is -1. It's in here. And how big will be the Gaussian? So how fat for the Gaussian? It depends on the covariance. It will look like as it's 5, so it will from -1 we will minus 2.5 to -1, and then plus 2.5 from -1 is like this, these 2 points. So that will be the graph for the first class. And for the second class, the mean is 2. And the covariance is 2. We can see the covariance of second class is smaller than the covariance of the first class. So the graph of class 2 will be thinner than the first one. It will be something like this. And the maximum value of the Gaussian is usually is this one. That's the maximum of the Gaussian. So we can plug in the 5 and 2 to here. Then we know the Gaussian of the maximum value of class 2 is higher than the maximum value of class 1. So the graph will be like this. This one is for class 1, and this part is for class 2. We don't need to draw that precisely. We just need to know the class 2 will be thinner than the class 1 and taller than the class 1. That's it.
Question here shows the refractive index.
For 1D, the second sorry, this one. This one should be the covariance. It's not standard deviation. So, oh, sorry, it's variance. So it's this sigma square. We usually like mu and sigma square. Yeah, I write it wrong in here, sorry. Covariance is for multi. Yeah, sorry about that. Okay, the second part, find the expression for likelihood ratio in terms of x. The likelihood ratio is just we write the likelihood of each case in the fraction form. So the denominator is likelihood of second class, and the numerator is likelihood of first class. We just write down like this, the ratio just write down like this, and plug in the, just write down the Gaussian distribution equation for each one. It will be yeah, I'm just going to write the formula because for the drawing, I don't think we don't use the formula. We know the main and the covariance and the variance, then we can draw the picture. But for the right now for the ratio, I can just write down the formula. So for the first part, it's the peak of the Gaussian is this one. The formula is this one. That's the maximum value for the Gaussian. And I didn't calculate for the exact value. You can just plug in 5 and 2 in this formula to see what's the value. Okay, so okay, I can write it again. Yeah, actually the value for the peak is just the equation like this one in here, just this part. Everything before the exponent. That's the value for the maximum value. That's the equation for the maximum value. Okay, so for the likelihood ratio, is this fraction, and we write down the Gaussian formula for it for each one, and then we just do the calculation, simplify. We can get yeah, we can just write down like this. Just simplify the equation. I don't think this question is very meaningful, but it's just like this. Okay. Let's go to the part C. Right, all of this is likelihood, and right now they told us the prior property is the same. So let's find the decision threshold. I just said the decision threshold is the when the posterior probability is the same, then we can find the boundary. So it's like this. We want to find the x to make the posterior probability for each case are the same. We want to get this. And right now we don't know the posterior probability. We can replace it by the likelihood and the prior. So we replace it like this. So we replace the first equation to the second equation, and it told us the prior probability is the same. So we get rid of this part. They are the same, so we don't care about it. So we just make two likelihood equal and try to find which x will make the two equation equal. So we just plug in the Gaussian equation for both sides. Okay, it's not 10. This step just plug in the Gaussian formula. And then we want to find the x. Right now, we need to take the log on both sides. Take this on both sides. It will become then because it's exponent and it's log, so we can get rid of both of them. This part is simplified as this. And we take the square out. This one's also get rid of the exponent and log. Become so I think from this part we can do the calculation, or we can simplify one more step. Is the mean value supposed to be square? No. That's the here's the mean value. And we take the x minus mean and the square of x minus mean. Okay, from this part, it's just simply calculate for x. I leave the calculate part to you, and the final answer will be something like this. And one is 0.38, one is 7.61, and we know that's the true boundary. And if you go back to the graph and write it, it should be in here. Okay, you will realize my graph is very not precise. It's something like this. It's not precise. So the two interaction, the first interaction of two Gaussian is 0.38, and the second interaction of two Gaussian graph is 7.6130. It's like this. Okay, I can just draw a better graph. Since we already know the boundary, what's the value should be the boundary. For the second one, the mean is -1. It's like this. For second class, mean is 2. Okay. This one is 0.38. This one is 7.6. Yeah, that's the true decision threshold. Part D, what's the probability of error under the decision threshold in C? So we want to find the probability of error. That means we want to find the probability of being classified multiplied by the prior probability. So we can write the equation like this. Error is so this one, the first part is we know it's class class 2, and then we classify as class 1, and we plus the second case we know is class 1, and we classify as class 2. So we sum up these two cases. The total probability is the probability of error. So because we know these two, we know the prior. Now we want to know the probability of classified. If we look at the graph, this one is probability density graph. If we look at the density graph, the probability of misclassified is the total area in the graph. We just want to calculate the area in the graph. Which area is the area that's being classified in the graph? So there are 3 parts that are misclassified. The first part is here. That's the area 1. And the second area is it's under the purple line and x bigger than 7.6, and then the area under the purple line. That's the area 2. And the area 3 is here. X is between 0.3, between 0.3 and 7.6. Also under the blue line. That's 3 areas that being classified. Area 1, area 2, area 3. So area 1 and 2 means we should, that's class 1 and that's class 2. For area 1 and area 2 means it should be class 2, but we classify it as class 1. For the area 3 it should be class 1, but based on the boundary, we classified it as class 2. So we need to find the area of all these 1, 2, 3. Okay, so for calculating the area, we just use the integral. For area 1, for A1, the integral is negative infinity to 3a70. That's the boundary. It's under purple line, so we should write down the equation for the purple line. So this integral will give us the area of A1. For area of A2, it's the same. So from 7.6 to infinity. And it's also under the purple line, so we plug in the equation for purple line. It's also the equation for class 2. We do the same for A3. A3 is bound by 2 boundaries. So the upper bound is 7.6, lower bound is 0.78. And it's under the blue line, so we plug in the equation for class 1. Okay. And these are the equation for area. It's also the equation for, we just said this that area equals to the likelihood. So we just put these three equations back to this equation, and we know the PW2 and PW1. We just plug in all the equations together. It will be, I just write it in here. For first one, it's we know PW1 and PW2 is 0.5. We know it's 0.5. So in here we do 0.5 multiplied by the integral. I just write A1 for simplify. That's the final equation. And we just want to calculate the final answer of this equation. It will be 0.0353. You guys can try it out to see whether you can get the final answer. For here, A1, A2, A3, just plug in this part into the A1, A2, A3. So every time we want to find the probability of error, we just go to the graph to see which part of error is being misclassified. Any question about this question? Sure, and I just answered the last question first. Why do I multiply each integral by 1/2? Because in this equation, I said it's likelihood multiplied by the prior. So the prior probability is 1/2. In here, it's we need to multiply by the prior. The area just the likelihood. And the final answer is 0.0353. I didn't use the integral twice. For each area, I just use once. For the area 1, I use once, and for area 2, just once. For each area, I use integral to calculate the area. And in here, I just adding up each area multiplied by, oh no, sorry. Actually, the thing is, here A1, I shouldn't use A1. Here A1. Okay. I shouldn't do this. It's not twice. A1, A2, A3. Yeah. It should be like this. So here, the A1 is the whole thing. here. It makes sense. It's not taking twice integral. Yeah, we found this. And one of students said, can I go back to part C? So what's the question about part C here? Okay, sure. So part C just make two, okay, good. Okay, let's go to next part. The next question is we see this one, we know it's multivariance. And we will think of, we have three cases for this kind of Gaussian. So every time we see this equation, we just think of, okay, we have three cases. We need to find which cases this one satisfied. Okay, so we just go to the part A. We assume the covariance matrix equal to identity matrix. So we know it's case one. And compute the G function for the follow data samples and then identify the class label. Okay, we know it's class one. So, sorry, we know it's case one. For the G function for case one is this. That's the G function for case one. And we just okay, I think in the question it says the prior property are the same, right? Yeah, in here. It says the prior property for both cases are the same. So we don't need to care about this part because like whatever class one and class two, we calculate, we add this part, we both add this part, but this part is always the same. So we don't need to add this part for the compare. We just erase this. Now the equation for the G function become only one part equation. So now we just expand this to, actually for this one, you can just write, if you don't want to know how it derive, how this equation derive. If you don't want to know how is this equation derived, you can just remember, okay, this formula is for case one. And why is case one is from here. The covariance is equal, matrix is equal to identity matrix. For the case two is variance matrix are always the same. they don't need to be identity matrix. That's case 2. And for case 3, it's whatever the covariance matrix is. Yeah. So from here, we know it's case 1, and we just go to find the equation for case 1. And explain, and we didn't care about this part, and we just expand the first part become so we know x for x1, we know x is 0.5, 1.5, mu1 is 3.1, mu2 is -2, -2, and sigma it's 1, because the covariance matrix is like this, right? So we know the variance is 1. Wherever it's variance 1 or variance 2 for variance for case 1 or variance for case 2 is always 1. Okay, we know that's for x1. We just plug in all this number to this equation. It will become, I just write first, 0.5, 1.5. Sorry, it's so G1 for x1 becomes, so G function for class 1 is this equation. And the final answer is -3.25. And for class 2, you just replace the mu bar, and yeah, because the variance is the same, so we just replace the main. The only difference is here. It's not 3.1, it's -2, -2. Here is okay, I write this wrongly. It's 3 and 1. And here has a negative sign because in equation there has a negative sign there. So the final answer is -9.25. So just in here we know the mu, the variance, we just plug in the number to this equation. And we got two numbers, to the value for class 1 and value for class 2, we know the G1 is larger than G2. So we say X1 is belong to class 1. For the class 2, for the X2, we just follow the same step for X2. Just replace this one to X2. X3 is given, it's -1, -1. Yes, it's ignorable because it says the question told us the prior probability of 2 cases are the same. We can calculate it. For example, we add this part back to the equation, but it won't change the result, right? Because these two are the same. Because prior probability for both cases are the same. We can just ignore this part. It won't affect the result. But if we say what's the equation for G function for case 1, we need to include this. The only way we ignore this because the question told us the prior probability are the same. For each case are the same. That's the only way. The total discriminant function G actually it's not the total, it's the here the G there has an I in there. So it's one discriminant function for class 1 and one discriminant function for class 2. So each class has one discriminant function. And we just calculate, or we just compare the value of these two discriminant functions. And we choose class 1 because it's close to 0 or more positive. We choose class 1 because the discriminant function of class 1 is larger than the discriminant function of class 2. In the class note, they ignore for the denominator for the equal prior. For you only can ignore the prior probability when the question states that the prior probability are the same. If not, you need to consider the prior probability. Yeah, if is the way we calculate the single discriminant function called y. Yes, we can just create a discriminant function gx equal to g1 minus g2. We can do that, but just for this question, they didn't do that. They just used two discriminant functions. So we just say it, each class has one discriminant function, just based on this question. Yeah. So for x1 is belong to class 1 because the discriminant function of class 1 is bigger. For the second, I just don't want to do it again. You guys to try, you can just put in the number and see it's the same. You just change the value for x, and we will see the x2 is belong to, this one is belong to class 1. This one will belongs to class 2. You guys can try to see whether it's correct. Okay, next one. Now the covariance change to here. Change to this one is no longer equal to identity matrix. Both of them are changed to this. And we know the covariance matrix for class 1 equal to covariance matrix for class 2. Then it's no longer case 1, it's case 2. Right? Like both case has the same. Both case has the same covariance matrix. It's class 2. Sorry, it's case 2. Okay, the G function for case 2 is and I believe there has one more. We also need to add this one, I believe. But it's the same because the prior probability is the same, so we just ignore this part. Okay, so that's the G function for case 2. And everything stay the same. Like the value of x1, x2 stays the same. The main is the same. Only the covariance matrix become. So we need to calculate this part based on the new covariance matrix. Okay, we just plug in all the number back to the equation, and we will get. Yeah, I just didn't do the calculation part. So the final answer will be like this. Okay, it's not. It's 1, 2. And G1 is larger than G2, so class 1 still equal to, sorry, X1 still belong to class 1. The question asks us, will the classification of class 1 change, X1 change? The result doesn't change. Okay. So justify is just computing, G1, G2, using the different equation to calculate the G1, G2 for X1. For part D, just calculating the G1, G2. This question, the thing they want to ask is, you need to know for part 1, part A is case 1, for part B is case 2. That's the only thing they want to ask. Because the the equation is already given in notes, but they just want you to know to identify which cases this Gaussian belongs to. Okay, any questions? If don't, let's just rest for 10 minutes. Let's go back at 4:40. Sure. I will ask the prof why they didn't make you guys to see the solution. But I will also go over the solution for the LDF later. Yeah, the question, the thing is, I don't know why they upload the first one, the solution for the Bayesian, not the linear. So I just asked why they didn't do that. But just if the reason is they forgot, so I will upload it. I just don't know why. I need to ask the prof why they upload it. Can we use an integral solver for the question, or are we only allowed to have the AZ table? So sorry, what's AZ table? You can use any calculation or any code helper during the midterm. The one I usually do is Wolfram Alpha. It's very powerful. For the, you mean the question 2? I didn't really see the solution, given solution. Yeah, I think, yeah, you can use any way to solve the question, because especially for midterm, you don't need to give us the steps, right? So it's either fill in the blank or the multiple choice. So we just want to know the final answer. I don't know if the prof told you guys the format of the midterm. If the prof doesn't say you need to provide an extra sheet about your steps, in the D2L you don't need to input any steps, just the final answer. The midterm question haven't finalized yet, so I'm not sure this one, but I will definitely tell other TA because I'm not responsible for creating the question for the Bayesian part. So I will just ask that TA to consider this part, consider this situation. But frankly, I think you just calculate the integral, solve the integral. It would be better. Like, because during the exam, you can use any kind of online calculator. It won't be take a long time to just input the integral equation. Yeah, no problem. For the integral, calculating the integral. Yeah, I just said like the final. Sorry, the midterm question is not finalized yet. I will ask that the TA who is responsible for creating the question to consider this situation. But for my advice is just calculating the integral, solve the integral, because you guys can use any online calculator during the midterm. So just plug in the integral equation and get the answer. It will be safer. The format of the exam is on D12, so all questions on D12, and it's multiple choice, fill in the blank, something like that. And I'm not sure if the prof asks you to provide the solution, like no solution, the step. But in D12 it doesn't. So in D12 you don't need to input any steps, just the final answer or the multiple choice. Okay, let's continue. The final topic is linear discriminant function. The format of the linear discriminant function is this one. And we want to find the best value of W0, W1, and W2 that makes all data can be classified. Like for example, there has a point like this. We want to find a linear line to make to classify these two parts of data. If the G function of this data, for example, we have a G function, and then we plug in all this part of data, the class data to the G function, and we get the result, the value of the G function is larger than 0. And then we plug this part of data to the G function, we got the value is less than 0. Then this G function is the one to classify all this data. That's how to use the G function. And to find the decision boundary, so to find the decision boundary, we want to let the G function go to 0. And then we can, it means this part is set to the 0, and then we can convert this part to a linear line, and where m is the slope, b is the y-intercept. Okay. Okay, so how to find the W0, W1, and W2? There has two important methods. One is perceptron gradient descent, and the other one is minimum square error. There are two major differences between these two methods. For the first one, the update for the perceptron gradient descent, it only considers misclassified sample. So we only use the misclassified sample to update the weight vector. But for the MSE, we consider all samples, whether it's misclassified or classified, correctly classified. We use all samples to update the weight. The second difference is the perceptron gradient descent use the perceptron gradient function, and the MSE use the square error criterion function. So what's these two functions? This one is the perceptron criterion function is this one, and the square So both method, each method use different error function to update the weight vector. That's the difference. And this error function and its integral are also in the course note. So just try to know, just review it to see the difference and the difference of their each error function, the integral of each error function. Okay, and perceptron gradient descent can be run in single sample or batch. So run the single sample, it means consider each sample data at a time. If a sample is classified, we calculate the error based on that single sample and update the weight vector based on that single sample. After the update, we repeat these two process again with next new sample. So we just, for each sample, we repeat these two steps and stop when all sample data are correctly classified with the same weight vector. So we got the final weight vector, and then apply on each single sample once and see all the sample are correctly classified, then we are done. Okay, that's single sample. And the other way is batch. Batch means consider all sample at a time. And we choose the misclassified sample and then sum all the misclassified sample together to update the weight vector. So we doesn't update the weights based on one sample. We base on all misclassified sample. That's the difference between single and batch. And just repeat until all samples are correctly classified. The stop condition is the same for both method. Okay, you guys need to know what is single sample and a batch sample. So this one is for the perceptron gradient descent. And for the MSE, the formula is just this one. And we replace the y plus to by this part. So we only need to know what is y, and then based on y, we know what's the y transpose and y transpose y inverse is all based on y. And then the b is always given to us. So based on that, we can just directly calculate the final w, final weight vector. Okay. And one thing is, y is the in here. Y is the normalized row-wise sample. It means each row. That's class 1. Oh, sorry. X1, X2, X3. So each row represents one sample data. That's you guys need to remember, because if you do like this, the final answer will be different. Okay, so it's y is normalized row-wise sample. And we got y, we can just calculate the final W vector. And one thing between the MSE and the perceptron is because we one thing is like we just said the MSE take all the sample data. We in this process we doesn't care about is this one is misclassified or classified. We didn't care about that. So we also don't care if these data are linear separable or not non-linear separable. Even though the data set are non-linear separable. For example, it's like this. That's class 1, and that's class 2. And here has one class 1 in here. So if the data set is like this, it's not linear separable. You cannot draw a linear line to correctly separate all this. The only way you can classify is like this, but you cannot draw a linear line. So that is linear. How do I say that? Non-linear separable. It's non-linearly separable. If we apply the perceptron gradient descent on non-linearly separable, we will see the process never stop. Because we say it stop when all data are correctly classified. Whatever is single or batch, they stop until all samples are classified. But for this case, there's no line to make all the data classified. So for this case, perceptron is we cannot use perceptron. But for MSE, we doesn't care because we only need the Y, then we can calculate the W. We can get the final W. Even though the final W, the final weight cannot make this one all correctly classified, but at least we have an answer. We can make this process work. So actually, so that's the third difference. Third difference is cannot apply on non-linearly separable data. And MSE is can apply. So that's the third difference. There are three differences between these two methods. Okay, so that's all the concept for the linear discriminant function part. So we go to the question. Okay. So the first question is they give us a boundary, initial boundary. And it says the boundary is passed through the point x5 and has a value on x2. So the boundary is passed through the x5. We know, actually we can write that as g x5 is equal to 0, right? And so we know there has two equation. G x5 is equal to 0, gx2 equal to 1. So we know the h0 satisfies these two equations. And the h0, the equation of h0 is w1 plus w2 w1x1, w2x2. And we want to find they ask us to find the discriminant function. So they want us to find the value for w1, w2, w0, and they also give us the value for w1. So here is 1. We have two unknowns and two equations, so we can calculate the value. It's 1. The x5 is these two, x2 is these two. So we just plug in these two value to the equation, become and we will get w1 become 0, negative 0.5, w2 become 0.5. So we will know the final g function is 1 minus 0.5x plus 0.5 x2. And they ask us the proposed boundary. So we know the function and we want to get the boundary, means we want to set this function equal to 0. Then we will get x2 equals to x1 minus 2. That's the boundary. And it wants us to draw it, plot the plane. So I just plot. Okay, I just first plot the point, plot all 10 points on the graph. It will be like this. We use green. I will use red color for class 1 and green color for class 2. Then the first class 1 is x4. So minus 1 minus 1. This one x4. Then 1 minus 1. 0.9 and 0.10, it's around here. Okay, there has 6 class 1. Okay, I miss class. I miss x8. It's here. Then I draw the points for class 2. Okay, so I think all 10 points is in here. And then we got the equation for the boundary is says the y-intercept is -2. Y-intercept is -2. And past the, it says past the point x5. Y-intercept will be, let's set y equal to 0, and then y-intercept, x-intercept will be 2. The line will, the boundary will look like this. Okay. Yeah, something like this. That's H0. And from this equation, we know the g function, the value of g function for x2 for this point is larger, is equal to 1, so larger than 0. Then we know this part is all larger than 0. Gx. And below then this line will be negative, will be less than 0. That's the boundary. Okay, so part B, what's the accuracy of the classifier? So what's the accuracy if we use this boundary to classify all the points? And state any assumption made. So we assume, like for this one, we just state our assumption first. We assume, because usually we say when g function larger than 1, larger than 0, we classify it as class 1. So in here it's W1. When g function equal to less than 0, we classify as class 2. When g function is equal to 0, we doesn't classify as we doesn't classify it as any class. We just say it misclassified. That's our assumption. If you made other assumption, you will get different result. But right now, that's my assumption. So all my accuracy is based on this assumption. Then based on this assumption, I should get, I know this part of the graph is larger, the value of g function is larger than 0. So then this part should be, okay, change color. This one should be class 1. And then this area should be class 2. So if I want to find the accuracy, I just find which color is the correct. In this area, in the class 1 area, all points should be in red. And in this area, all points should be in green. So I see in the class 1 part in the points in red color has its class, sorry. It's S4, S8, S9, X10. That's the points in X1 area and with red color. And for the X2 area, for the class 2 area, I didn't see any points in green color in here. So there's no points. It's correctly classified in this area. So total is 10 points, and I got 4 points correctly classified. The accuracy will be 4 divided by 10, 0.4. I solved this question by looking at the graph, but you can solve it by using the G function equation. For example, we have the G function equation, this one, and I just plug in the value of, for example, x1 to it and see whether it's larger than 0 or less than 0. You also can do it by that. Just because I draw the graph, so I use the graph to see whether it's correct. And all this accuracy is based on my assumption. If I assume if I assume when the value of the G function is larger than 0, then I classify as class 2. All the results will be different. Any questions? If no, I go next. Okay, I go to part 3. The part 3 gives us a training set. It contains 4 points, and we use that to build a classifier based on the perceptron error, perceptron gradient descent. And it told us we will run it for 3 iterations and in batch mode. So that's important, which mode. It's either single sample mode or the batch mode. That's important. Okay, and it gives us the learning rate and asks us to plot the new boundary. Okay, we just run the perceptron first. The first step, we need to perform the argumentation and the normalization to the data points. The select data point is x1, x3, x4, x8. Then it becomes 1, 1, 1, 3, -1, -1, -2, -1. And we apply the normalization. And, it's argumentation. And then after the normalization, we see x1 is class 2, x3 is class 2, x4 is class 1. It's class 1, so we change the sign of the class for x1 and s3. So right now, after the normalization and the normalization and the argumentation, we got this matrix. The second step, we need to get the initial weight from the initial boundary. So we just calculate the initial weight from the part A. The initial weight is W1 is 1, W2 is how much? This W3, W1 is negative 0.5, W2 is positive 0.5. That's the initial weight. Okay, it's add T to it. Now we start the perception error update. Since we are in the batch mode, so we need to multiply the weights to all select data points. We don't do it one by one. For the first iteration, we apply the weight to all data points. And then I will get just this calculation is simple, right? This vector, apply this vector, I will get -1, -2, 1, 1.5 for each vector. Yeah, so I get four values. And from this 4 value, I can see the first point and the second point is misclassified. So I need to use these 2 points to do the update. We know the update rule. The update rule for weak vector is K is the iteration. A is the vector. We should say W, but in here we use A. And this one is the learning rate. That's the update rule. And it's in batch mode. So here we have a summation. So we need to sum up all the misclassified points. In the first iteration, there has 2 points. So we need to sum up all the first 2 points as this part. Therefore, we just plug in the number to it. It will become, let me do this. A1, because original K equal to 1, because now it's only the first iteration. AK means A0, and the learning rate is 0.1 is given by the question. And we need to sum up all misclassified points. That's X1 and X3. Okay, so we just calculate it. A1 just the first initial weight. If we want to use, oh, okay, you can also write it as this one. If you want to use minus y, actually the equation should be like this. Here is minus, and y is minus y. The original equation is this, but we can just take the minus sign off, become plus. Is that clear? So here I just use the plus. Okay, good. But original function is minus, because if you only because you use the perceptron criterion function. If you use the square one, if you use another criterion function, when we apply this update rule, it's minus here. Why do I normalize by making the class 1 class negative? Actually, no. In the question, x1 is class 2. So I still made the class 2 negative. Okay, so after this, the answer is 0.8, negative 0.7, 0.1. Okay, this one is the new weak vector after the first iteration. So we use this vector for the second iteration by computing like this. Y, just the same Y I used using the first iteration. And after this, we just to see which points are still misclassified, and we just summing up all the misclassified points and update the weak vector again. So, okay, I won't do for the next 2 iterations, it's the same. After the 3 iteration, A3 is 0.5, oh sorry, 0.6, negative 0.9, 0.3. You guys can try it off to see whether you can get this result. And one thing, if the question asks you to do 3 iterations and you found that, oh, actually the question will not ask that, so never mind. Okay, so you have the 3. After the 3 iteration, you got this weight vector, and the question asks us to plot the new boundary. So we use this weight to get the new boundary. It's 0.6 plus, sorry, subtract 0.9 x1 plus 0.3 x2 equal to 1, because we want to get the boundary. Then we will get the new boundary as 0.x2 equal to minus 3x1 plus 2. And plot the boundary to the graph. Okay, I just don't, you guys can plot it because you already got the boundary equation. And part D, based on your calculation from part C, will you expect the single sample method to yield a better boundary than a batch method? After seeing all 3 training patterns just once. Actually, the question is asks us whether the single sample method is better on the batch, or batch is better than the simple sample. Actually, whether we run it in the single sample method or we run the batch, both methods do the same thing, because both methods visit the sample points just once. Right? Therefore, the boundary result from the both method will be will have the same quality compared to each other, because all methods just visit each sample once. So here I will answer, it won't be you a better boundary. The quality is the same. However, the one thing is you run it by batch for one iteration, or you run it the same single sample for all sample ones. The result boundary may be not the same, but the quality is the same because you just go through all points once. For the first iteration, we knew which are misclassified because the value are negative, yes. So in here, because it's -1 or is less than 0, so we said it's misclassified. If the G function is, because we normalized it, right? In here, we normalized it. We made all the points to belong to class 1. So in that case, all the G function value, the value of G function should be larger than 0. So if some points the value is not larger than 0, we said it's misclassified. Does that make sense? Okay, good. Next question. If all 10 samples from question 1 are used in training, in here you just in Parsi you just choose 4 points. Let us to do the perceptron on the 4 points. In the question 2, it says we need to use all 10 points, all 10 samples for the training. Which following approach would be a more suitable technique for building a classifier? Okay, from the graph, this graph, we will see these samples are not linearly separable because there has a x10 just very close to class 1. Very close to the green points. So actually we cannot find a line to classify all the points correctly. For example, we put a line like this. Still, the x10 is misclassified. So this one is the example that the sample points are not linearly separable. So as I just said, if we apply the perceptron gradient descent on all 10 samples, the algorithm never stops. So because it cannot, we cannot find a line to classify all points correctly, it will be the same situation for the relaxation. For relaxation, just apply another. Right now, it told us we don't use the perceptron error criterion. We use the normalized square error criterion. We just use another criterion, error criterion, but the algorithm are the same. So the relaxation still cannot stop because we cannot find the line. However, the LNS, the least mean square, can handle the nonlinearly separable case. Also, the MSE can handle the nonlinear separable case. So we choose the linearly, the least mean square in this case, in this situation. This one never stop. Okay. Final question, number 3. A new training data set is follow points. Okay, this point we choose another 5. So these 5 are also from the question 1. It's also from this part. We choose these 5 points as a new training data set. And right now we use the pseudo-inverse matrix. Pseudo-inverse technique, which means we use this one, this technique. So I just write down in here. We use these 2 equations to compute a value for argument vector A. Okay, we use A, so I change back to A. Assume BI equals 1 for all I. So it gives us the value for B. It's already, it has 5 points, so the vector B will be 5 value, and it's all 1. That's what will be like. Okay, and show all the stage working. Because it's practice question, it says you can use MATLAB. For the midterm, you can use any like online calculator or MATLAB. But the only thing is, like, you just choose the one technique that you can spend less of time, the least of time you can use. Okay, so for this one, we have the equation, we have the B. Right now, we just need to select just need to find the Y. Y is from the training points. So Y, the select training points x1, x2, x4, x7, x8. And Y will become, I just said the Y is, Y need to be normalized and the row vector. Oh, sorry, row wise vector. So should be like this, right? So if I write it in number, it should be 1, 1, 2, 2, -1, -1, 3. Okay, and I just do the argumentation and the normalization. Y will become okay, that's our Y. And then from here, we can know the Y transpose is column-wise sample. Okay. Now we have Y, and we have Y transpose. We just need to do, all we need to do is plugging the Y and Y transpose into this equation to find the Y plus. You can use MATLAB or Wolfram Alpha. That's the one I like most. it can compute everything. Okay, eventually you will get, after you got the y plus, and then you can just multiply by b, but the b is all 1, so it's the same. So eventually you can get the a is and that's the weak vector, and we want to write it as g function. Okay, that's the g function. The question asks us to plot the hyperplane. So actually we just need to calculate the boundary. So we set the g function as 0. And we will get something like that's the boundary, H3. And part B, give the value of the discriminant and comment on the resulting classification for each the following. So we got the g function and we got the points. We want to know the classification result of each point. So we just plug in the data. For example, plug in the x1. What's x1? x1 is 1, 1 to this g function. Or for x5, it's 1, -1. When I plug in, it should be it's 1, and now become plus. And this will get something like 0.4410, which is larger than 0. Then this g function will classify 5 as the x5 to belong class 1, which is correct in here. It's class 1. Okay, we just repeat this process for each point, 4 or 5 points. And we will see after the plugin, we will see the result will be x5, x7, x9 are correctly classified. I think the class 1 is also classified. Yeah, like the only one cannot be the only one is misclassified is x10, because the x10 is too close to because the graph is like this. The x10 is too far away from its original class. So we got the g function and we plug in all 3. Oh, sorry, it's not class 1. We should plug in we should plug in this 4 points. We should only plug in x5, 7, 9, 10. So we will get x5, 7, 9. It's correct. x10 is wrong, but we still say this result is acceptable because we know in this one we cannot, it's not linearly separable. We cannot find a boundary to have 100% accuracy as long as the error rate is small enough for the unseen data. Because we use these 4 points for these 5 points for training, right? So these 4 points are unseen or testing. As long as the error rate is small enough for the testing data, we say this boundary is good enough for generalization. Also, this question proves that the MSE can be applied on the non-linearly separable case. Okay, any questions? I think, yeah, we are done for the practice problem set. Any questions for both problem set or regarding to the midterm? Is share the notes. Okay, yeah. For the solution, I can. Do you guys want the draft? I think my writing is so. Okay, I can post the draft. Sure. And what's the purpose of the argumentation step? Argumentation step is, we can see in here, we add one more degree to it, because we will, in weight, we have bias weight, right? We have W0, W1, W3, 2, we have a bias weight. So in the sample, we have we add argumentation. We do the argumentation to add one more degree for the bias weight. We do need the normalization for the MSE. So right now you can see here. Let me change the color. It's negative. And here is 1. Okay. Sure. I will post the draft, and I think I will post the question for, sorry, the solution for the practice, for the LDF practice. All the non-calculating question and the justification question, all the solution are in the, I think they are already stay in the solution. Like they provide a solution for the justification part. Okay, any other questions? Good. If no, good luck to your exam. Like you guys need to start right at 3:10. because the exam is closed right at 5:10. Yeah, thanks guys. Good luck. Yeah, I will stay for maybe a couple minutes to see anyone has other questions. And if not, you are free to leave.